This is the class lesson for section 5.2, part 1, and we will be talking about power and polynomial functions. So I just thought we would work these in groups. I think it's important. We can look at them all at the same time. So I'm actually going to work 6 through 11. So let's look at number 6. This number 6 is definitely a power function. We have a variable raised to a power. Looking at number 7, if you simplified that, you'd have x to the 6th power. That's also a power function. It is a variable raised to a fixed power. And in number 8, if you look at that one, we don't just have a single variable raised to a power, but we have several added and subtracted together. So this is a polynomial. Okay, so some of these are power functions and some of these are polynomial functions, okay? Looking at number 9, this is neither polynomial nor power, okay? This doesn't have variables raised to powers added and subtracted together. They're actually divided. It's a rational function. Okay, think about this. Think about multiplying, squaring x minus 1, and then multiplying it by x plus 2, and then distributing the 2x. Eventually, you will have coefficients with variables raised to powers. So this is a polynomial. Now, look at number 11. We don't have a variable raised to a fixed power. We actually have a number raised to a power. So this is neither. And you know what I might do? I might just go ahead and tell you what it is. This is an exponential function, and we'll be talking about that later. And this is a rational function. But both of those are neither power nor polynomial. Okay, for the following exercises, find the degree and the leading coefficient for these polynomials. So we're going to start with number 12, and this is how I am going to abbreviate this. We're going to use n for the degree, and for the leading coefficient, we're going to write a sub n, okay, for each one of these. So for 3x, the degree is 1, and the leading coefficient is -3. Don't forget, this is x to the first power, and that coefficient in front of an x raised to a power is a -3. Let's go to number 13. We're looking for the term with the highest power of x, and it is this term right here. The coefficient is -2, and that degree is 2. So we can actually say that the degree is 2 and the leading coefficient is -2. Okay, likewise, let's go ahead and find the term with the highest power of x. That leading coefficient is a -3 and that degree is 5. Looking at number 15, now you have to think about multiplying these together. So I want you to think about this. I want you to think about taking a negative x squared and multiplying it by a 2x, okay? You're going to have an x cubed. And then you have another x, so you're going to have an x to the 4th. We're going to go ahead and multiply these out, but I just want you to see, just in case somebody asked you for the degree, you would have 1, 2, 3, 4, okay, when we multiply it out. But we're going to go ahead and do that. Okay, the first thing I'm going to do is I'm going to go ahead and multiply the two binomials together. So we have 8x plus 4 minus 2x cubed minus x squared. And now let's go ahead and bring that x in, 8x squared plus 4x minus 2x to the fourth minus x cubed. So what do you notice? Here is our term that has the highest power of x. So the degree is 4 and the leading coefficient is -2. Looking at number 16, let's try this again. Do you see this square? So this x will be squared and then multiplied by x squared. We're going to have a degree 4. Let's go ahead and multiply them together just to be sure. So we're going to multiply 2x minus 3 multiplied by 2x minus 3. We get 4x squared minus 6x plus 9. Let's go ahead and take a simplification step, combining the outer and the inner. And now let's distribute that x squared. Okay, what do you notice? There is your term with the highest power of x. So our degree is 4 like we thought, and our leading coefficient is 4. Okay, let's go ahead and take a look at number 17 through 22. We're going to talk about the end behavior, and I'm going to do a couple of different ways, okay? Let's look at number 17. This is even degreed, n is even, so both ends go up or both ends go down, one or the other, okay? I just want to talk about that. The leading coefficient is 1, which is positive, so both ends go up, okay? So let's go ahead and write that. N is even, A sub n is positive. So both ends go up. Now, how would we write that? Okay, we need to talk about how we're going to write both ends go up. But that's a nice little figure. Maybe I'll put that just to the left here. The left end goes up and the right end goes up. Kind of behaves like a quadratic. So how do we describe that? As x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches infinity. Okay? So I'm wondering if I should move all of that over here a little bit so I'm not in the way of that other problem. Okay? So that's that. Let's go ahead and look at number 18. So the degree is odd. N is odd. And the leading coefficient is positive. So when you have an odd degree, you either have right end up and left end down and whatever's happening in the middle, or left end up and right end down. One or the other. The ends behave like the ends of a cubic. So if n is odd but the leading coefficient is positive, you can see how this would be going up like a positive line. Okay? So how would we describe that? I'm going to change pen colors here. Here, the left end is down and the right end is up. So over here, as x approaches positive infinity, f of x approaches positive infinity, those y values. And now let's take care of this part right here. As x approaches negative infinity, f of x approaches negative infinity. Okay? So I really kind of wrote into another problem here, kind of running into that issue here because I just took this right out of the book. But I really wanted to do these with you. Okay? Number 19 isn't too bad. I'll go to a purple pen just to keep them separate. Here we have A sub n is negative and the degree is even. So remember, when you have an even degree, the ends behave the same. But this time, both ends go down. So as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches negative infinity. So the y values are both going to negative infinity. Okay? Sorry about not having a whole lot of room. Let's look at number 20. What do you notice? You notice that n is odd, that's 9, and the leading coefficient is negative. So what's going to happen is it's going to look like this, the ends. Think of a negative slope, okay? So and what will be is left end up, right end down. So as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches positive infinity. Okay? So let's look at number 21. We have, let's see if I can change colors here. We have the degree is even, so the ends are going to be the same. N is even, and the leading coefficient is negative. So both ends are down. So as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. The y values are both going to negative infinity. Number 22, here this degree is even and a sub n is positive. 3 is positive. So here we have both ends up. So as x approaches infinity, the y values approach infinity, and as x approaches negative infinity, the y values approach infinity. Okay, let's look over here. Let's go ahead and multiply this out. This is equal to 2x to the 5th minus x cubed plus x squared. We note that this is our degree, our highest powered term. So that is the degree is odd and the leading coefficient is even. So the ends behave oppositely, but this means the ends behave like a line with positive slope, or you can say like a cubic, okay? So we can make a little end behavior diagram. So the left end goes down and the right end goes up. So as x approaches positive infinity, f of x approaches positive infinity. And as x approaches negative infinity, the y values are going to negative infinity. Okay? And let's look at number 24. Okay. In number 24, we would have, if we would multiply this out, we would be able to see that the leading coefficient is eventually going to be negative. Okay, if you would multiply this out. So the degree is 7 and the leading coefficient is negative. So we have the left end up and the right end down, like a line with negative slope. That's what the ends behave like. So as x approaches positive infinity, f of x approaches negative infinity, and as x approaches negative infinity, the y values are approaching positive infinity. Okay? Okay. The last part of this lesson is counting the number of turning points. I see 1 and I see 2. I see 1, I see 1, 2, 3, 4. So the number of turning points is 2, the number of turning points is 1, and the number of turning points is, that looks like 4, okay? So what do? I think everybody can pretty much count turning points. It's when the graph turns from going from positive infinity to negative infinity, or you can just say going from down to up. So let's write a little sentence here. The degree n, a polynomial of degree n, will have at most n minus 1 turning points. Okay? So, since this has 2 turning points, the least possible degree is 3. The least degree, when you have 1 turning point, is 2, right? Take the degree, n minus 1. So 2 minus 1 is 1. 3 minus 2 is 1. 3 minus 1 is 2. So we're subtracting the degree from the turning points. Or you could say you're adding 1 to the number of turning points. So the least degree, add 1 to the turning points, is 5. And that concludes this first part of